Hi everyone, my name is Vanilla Akula and I'm presenting our CSCE 26 short research paper, Think, See, Prove, a constrained LM narration framework for embodied math tutoring. This is joint work with Abhishek Jariwala, Nayanika Reddy Rasholi, Daniela Magitu, and Richard Chapman, all at Auburn University. The idea behind this work is simple to state, but it turns out to be surprisingly hard for language models to get right. When an AI tutor teaches a student math, we care not only about whether the final answer is correct, but about how the explanation is delivered, in what order, and with what pacing. So the goal of Think, See, Prove is to constrain how the model explains, one step at a time, and to ground every one of those steps in an interactive 3D simulation. Over the next 20 minutes, I'll cover the motivation, the framework, and its mechanisms, a live demonstration of the running system, and the experimental evidence behind our claims. Let me start with why structure matters at all. In middle school math, the order of an explanation is just as important as its content. A skilled human tutor introduces the concept first, works through the calculation second, and confirms the answer only at the end. That ordering is not an accident. It reflects how people actually learn. Cognitive load theory explains the first half of this. When you compress the concept, the working, and the final answer into one dense block of text, you overload the student's limited working memory, and comprehension drops. Worked example: research explains the second half. Revealing the answer too early short-circuits the self-explanation effect, the moment where the learner reasons toward the result on their own. That moment is a large part of why step-by-step tutoring works better than simply handing over a solution. Now, large language models are remarkably fluent, and at first glance their explanations look great, but when we examine them closely, we found they systematically collapse this structure. They over-explain in the introductory step, they reveal the final answer prematurely, and they surface internal, implementation-specific notation, variable names that are meaningless to a student. So the fluency is there, but the pedagogical structure is not, and that gap is exactly what we set out to fix. Here is the problem in one concrete example, a simple fraction addition. A typical single prompt baseline may give a correct explanation, but it reveals the final answer right there in the very first sentence. In our failure taxonomy, that is failure mode 9, jumping ahead, these single prompt responses also often run long and blend all the stages together, which is failure mode 6, over-explaining. The constrained version instead separates the same lesson into 3 distinct beats. Introduce the concept, then show the calculation, then confirm the answer. The important framing here is that we are not merely asking whether the arithmetic is correct. The baseline's arithmetic is usually fine. We are asking a different question. Does the explanation preserve a useful pedagogical sequence? A single prompt gives the model almost no control over where the concept ends, where the calculation begins, and when the answer should finally appear. This motivates 3 research questions. First, to what extent can architectural constraints improve the structure of LM-generated tutoring explanations compared with a single prompt baseline? Second, are those improvements consistent across different mathematical topics and across independent model runs, or do they depend on luck and sampling? And third, what additional role does deterministic output validation play in supporting these constraints? Throughout the paper, our scope is deliberately narrow and specific, with intern explanation quality, meaning how a single tutoring explanation is sequenced, rather than how a whole dialogue unfolds. Briefly, let me place this in the context of prior work. Language models have been explored extensively for educational tutoring, and they can generate fluent, pedagogically relevant explanations. However, most evaluation of tutor quality relies on human judgment or on dialogue-level coherence, how an entire multi-turn conversation flows, rather than on how a single explanation is sequenced within one turn. From cognitive science, there is strong evidence that unstructured explanations increase cognitive load, and that worked examples, self-explanation, and step-by-step feedback all improve understanding relative to holistic responses. Separately, research on automatic question generation and on using an LM is a judge has shown that symbolic accuracy alone is insufficient for effective tutoring. So across these threads, the common gap is a lack of attention to within-turn explanation structure. That is precisely what this paper targets, and to make it measurable, we define failure modes for whether a response preserves the intended sequence of concept, calculation, and confirmation. Our framework rests on 3 ideas. The first is that Python goes first. Before any language model call is made, Python computes every mathematical fact the lesson needs. Common denominators, simplified values, intermediate quantities, object counts, and the final answer. The model is therefore never responsible for arithmetic. Its only job is language. The second idea is role separation. Instead of asking one call to explain everything, we split the explanation into 3 role-specific calls. Think introduces the concept only. C explains the calculation. Proof states and confirms the answer. Each call is given an explicit role and a set of constraints, and crucially, the answer keys are hidden from the think and see calls, which I'll return to on the next slide. The third idea is shared grounding. The very same verified facts that go into the prompts also go into Kapiliasm, our 3D simulator. For each step, it freezes the scene, places objects, and performs an action, using identical counts and totals. Because narration and visualization read from one shared state, they are grounded in the same verified state, reducing mismatch. And we use a single open-weight model, Llama 3.8b, on an NVIDIA A100, precisely so that we isolate the effect of the framework itself rather than the raw power of the model. Let's look at the mechanism closely, because this is really the heart of the method, and it uses 2 complementary defenses. The first defense is the role prompt. Each step gets explicit instructions. For the think step, the prompt reads, roughly, you are introducing the concept only. Do not show calculation or reveal the answer. Use plain English suitable for a middle school student. Keep it to 2 or 3 sentences, and do not use variable names, code, or simulation terms. But a prompt alone is not enough, because models don't always obey their instruction. So the second defense is input filtering. Before the think and see calls, Python removes the answer revealing fields, specifically the simplified numerator, the simplified denominator, and the result from the working dictionary that the model receives. Only the proof step receives the complete dictionary, with the answer included. This matters because it turns a soft request into a hard guarantee at the input level. The model can only narrate what is actually given. If the answer fields are physically absent from its input, this reduces direct answer leakage, no matter how the prompt is phrased. That is the core structural defense against premature answer reveal. On top of the role constraints, the constrained system adds a deterministic safety layer built from 4 rule-based checks. The first is a minimum word count. Any output shorter than 8 words is rejected as too thin. The second checks for internal variable names, using regular expression matching against tokens, like N1, D1, SN, and SD. So implementation notation never reaches the student. The third matches against a fixed list of disallowed phrases, and additionally flags any output that does not end with sentence terminal punctuation as truncated. And the fourth, applied only to the proof step, confirms by substring search that the final answer is actually present. When any check fails, the rejection reason is appended to the original prompt as a corrective hint, and the step is retried exactly once. Importantly, the baseline system has no validator at all. That deliberate contrast is what lets us answer our third research question. And as I'll show later, the validator catches real structural violations that the role prompt alone lets through. Now here is the system running end to end. On the left is Copiosum. It renders the verified quantities directly. 5 tiles, 4 of them colored, and the fraction 4/5 displayed in 3D. On the right is the lesson interface, showing real narration produced by Llama 3.18b for the question, which is bigger, 4/5 or 1/5. You can read the 3-step cards as they appear. Think introduces it. This is a fraction comparison problem, and we look at the numerators, the numbers on top. C does the reasoning. The denominators are the same, so we compare 4 against 1, and 4 is greater. Proof confirms it. 4 colored tiles out of 5, so 4/5 is bigger than 1/5, because 4 is greater than 1. And here is the single most important property of the whole system. The numbers you see on the screen and the numbers you hear in the narration come from the same Python state. The tutor is less likely to contradict the simulation because both are reading identical, verified facts. The interface makes the concept calculation confirmation sequence visible to the learner, and the shared grounding keeps the words and the visuals honest with each other. To measure structure rigorously, we defined a taxonomy of 15 failure modes. 6 of them are objective, meaning they can be scored with deterministic rules and require no human judgment. Failure mode 1 is wrong numbers, the answer absent or incorrect in the proof step. Mode 3 is wrong strategy, an incorrect approach for the question type. Mode 4 is hallucinated steps, an incorrect explicit arithmetic claim. Mode 6 is over-explaining, any step exceeding 100 words. Mode 7 is under-explaining, any step under 10 words. And Mode 9 is jumping ahead, the final answer stated in step 1 or 2. The remaining 9 modes are more subjective. Things like invented visuals, wrong analogies, repetition, narration simulation, mismatch, broken narrative, inappropriate confidence, negative framing, age-inappropriate vocabulary, and cultural assumptions. Assessing those reliably requires human annotation, simulation logging, or a validated judge-based protocol, so we reserve them for future work. In this paper, we report results on the 6 objective modes, which we can evaluate at scale and reproducibly. Our evaluation is a controlled comparison. Both systems, baseline and constrained, are tested on the same 100 generated questions. Those come from 5 topics: fractions, ratios, decimals, percentages, and probability, with 5 subtypes per topic and 4 questions per subtype. Both systems receive identical inputs for every step: the question text, the object, the action, and the Python verified working dictionary. The only variable we change is the role instruction at each step. The baseline uses a neutral single prompt instruction with no validator. The constrained system adds the role prompts, the answer key filtering, the validation checks, and 1 retree. The model is Llama 3.8bb, running on an A100, with temperature 0.7 and TOPI 0.9. Each system generates 300 outputs per run. That's 100 questions evaluated at 3 rolls each. And we repeat the entire procedure across 2 independent runs to check that the results are not an artifact of a single sampling seat. Now the results, which answer our first research question directly. Over-explaining is the headline finding, and it is dramatic. The baseline system exceeds the 100-word threshold in 85 of 100 questions. The constrained system reduces that to just 12. That is a 73 percentage point reduction, and it reflects the model no longer collapsing the distinct pedagogical phases into one long block. A mature answer reveal, failure mode 9 drops from 60% down to 33%. That is a solid 27-point reduction, but I want to be honest that it is only a partial fix, not a complete one. The reason is that the answer can still be implied indirectly. A phrase like dividing both by 4 gives 1/2 communicates the answer without ever writing the fraction, and our keyword-based detector does not catch that. So, the 33% residual is partly a limit of rule-based detection. One further result worth highlighting: hallucinated arithmetic failure mode 4 is 0% in both conditions. That's because the model never performs the math Python does, so there is simply nothing for it to get numerically wrong. That is the direct payoff of computing verified facts before any narration. Breaking the results down by topic addresses part of our second research question about consistency. On the left panel is over-explaining per topic. The reduction is essentially complete for fractions, ratios, and percentages. 18 down to 0, 16 down to 4, and 16 down to 0, with only a small residue remaining in probability, 18 down to 6. On the right panel is jumping ahead per topic. Here the reduction is real, but noticeably less uniform. Fractions and probability both drop sharply. Percentages, however, are the hardest case, moving only from 17 to 14, and decimals are also stubborn. That's consistent with the earlier point. Those are the topics where the answer most naturally leaks through indirect, conversational phrasing that our detector undercounts. So the takeaway is that the framework's benefit is broad and robust across topics, but it is not perfectly identical everywhere, and the residual difficulty is concentrated where implicit answer disclosure is easiest. Let me zoom back out to summarize research questions 2 and 3 together. On consistency, across the two independent runs the reductions are stable. Over-explaining ranges from 82 to 85 in the baseline versus 3 to 12 when constrained. Jumping ahead is exactly 60 in both baseline runs and 20 to 22 constrained, so the improvements are robust to temperature sampling, not a one-off. On the validator, it genuinely earns its place as a deterministic safety layer. It triggered a retry on 32 of 300 steps, about 11%, and those retries were concentrated at the calculation step, where variable names and calculation shorthand tend to slip in. Steps 1 and 3 each triggered only a handful. Almost every retried step produced an accepted output on the second attempt, and no step needed more than one retry. The key insight is that an output can fully satisfy the role prompt and still fail a structural check, a truncated sentence, a residual variable name, or a missing final answer in proof. And the validator catches exactly those cases that prompting alone lets through. I want to be clear about what this work does not yet show. First, we measure explanation structure, not student learning outcomes. Whether improved structure actually translates into learning gains for middle school students is an open question that requires a classroom study. Second, all of our results use a single open weight model, so they may partly reflect Llama 3.8b's particular instruction following behavior, and larger or weaker models could show different magnitudes. Third, our failure mode 9 detector is keyword-based, so it likely undercounts implicit answer reveal, meaning the true premature answer rate may be somewhat higher than 33%. And fourth, while the demonstration visibly aligns narration with the simulation, we do not yet log the copilism state and verify that alignment automatically. Accordingly, future work runs in 4 directions: a human plus LLM judge protocol for the 9 subjective failure modes, validated with a Cohen's kappa of at least 0.7 before we apply the judge at scale, evaluation on larger and more diverse open weight, and most importantly, classroom studies that measure real learning aims. Finally, to support reproducibility, all of our code, prompts, validation scripts, and experiment configuration are available in our public GitHub repository, linked here on the slide. To conclude, think, see, proof demonstrates that explanation structure and mathematical correctness can be jointly constrained during generation, using role-specific architectural instructions, rather than simply hoping that a single prompt behaves the way we want. The system separates concept, calculation, and answer confirmation into 3 roles, grounds every narration in Python-verified facts, and connects those same facts to a copilism 3D visualization animation, so the words and the animation always agree. In our evaluation, over-explaining fell by 73 percentage points, and premature answer reveal by 27, both replicated across 2 independent runs. And our 15-mode failure taxonomy, together with a deterministic validator, gives the community a reusable, objective way to assess within-turn explanation quality, which is distinct from the dialogue-level evaluation that most prior tutor work has focused on. The broader message is this: for educational language models, correctness is necessary, but it is not sufficient. The explanation path itself, the order in which understanding is built, needs to be deliberately designed, constrained, and measured. Thank you very much for watching.